Tuorla Observatory, and he will talk about quasi-sphericals, as you can see. So, yes, please.
Thank you very much. So, my talk, the name is really Quasi-spherical. Soon you will see or hear that why that kind of name.
I am a quasi-spherical.
You are quasi-spherical, yeah. Then there's basic collaboration. There's some people which are related to this work, and you see the names here. And then there's at least 3 papers now published which related to the same topic in some level at least. So let's start this kind of idea or discussion about the definition of the superclusters in general. We know that we have observable objects, easy observable objects, clusters and galaxies, which are very, their fractional overdensities are very high, million times over mean density. And those clusters and galaxies are they are virialized and bound systems. And they also they produce some very homogeneous group of objects in some level. If we think about the size and richness, luminosity and morphology of those objects, they are variability between them and variation, but in principle they are, because they are virialized, they are some level very similar, and they are well defined. But superclusters are something else. They are only few times of the mean density, so it's very difficult. They are not virialized. And if you can define somehow superclusters as object, they are very heterogeneous if we look at the properties of the superclusters. They are clumpy and their morphologies are very different and so on. So they are not definitely similar type of an object at least. So they are not well defined. So they are different definitions used, and most simple probably is this number density field, where you just calculate the general number density field of galaxies, and then you put some limit and define, say that all the objects about some few times of the mean are, for example, superclusters or some kind of regulation limit, something like that. Then somewhat little bit advanced method is luminosity density field, which take account the luminosity of each galaxy, and each galaxy is weighted with that luminosity, and same time we keep in mind that probably this luminous matter reflects somehow also the underlying dark matter distribution. Then there are more light managed methods or more difficult methods, let's say. For example, coronal tessellation and inner filtering methods, which are somehow some people more like topological, at least this coronal tessellation method. And then there is a dynamical definition, which is the one way to define superclusters. And recently there was a Tuorla et al. Who defined local Laniakea superclusters using this dynamical definition. But our idea or purpose in this paper is study dynamical situation in superclusters, but the question is, what is the dynamical state of the superclusters defined with luminosity density method? That is actually the basic question probably in this study. The dynamical definition by Tuorla et al. Was this seen in this figure, and that is the area in these are physical units. That is the area which is defined that way, that it's a region where surrounding galaxies have still outside of this orange border, that is like a subtle, that kind of diverge region, or the region where here, if you have galaxies here, then they are along the Hubble flow completely. There's no peculiar velocity, or the peculiar velocity, if it exists, it goes toward some other center of mass nearby, probably another supercluster. So that is the definition of the Tuorla of the supercluster Laniakea. Okay, in principle, this sounds quite nice definition. It's also some level it's well defined, but the problem is, of course, that we do not have this peculiar velocity information only for our local universe, and this cosmic flow 2 catalog, where these galaxy velocities are taken, it's actually surprisingly deep. It's something like 80 megaparsecs or something like that. But anyway, it's anyway restricted by region. Now one question here could be that how we can, if we do not have these peculiar velocities, how we can study dynamical property of the, for example, superclusters without this knowledge. And here we use this kind of approach that we starting from the cosmological current, cosmological paradigm or knowledge that we have the dark energy density is global and it's everywhere and it's dominates uniformly across the space. And in standard lambda CDM model, it acts like a repulsive force. The space itself is expanding, and the gravitational there's a repulsive force which accelerates and expand, cause the acceleration and expansion of the universe, and then we have locally forces to the other direction which comes from the gravitation. And in those regions where the dark energy dominates over the gravitation, regions where dark energy do not dominate over the gravitation, other structures do not grow. So where it's not the dark energy is not large than the gravitational force, then the expansion is halted in that region. And now we know in general cosmological picture, we know that it's divided to radiation dominated, matter dominated, dark energy dominated region, and we are now just reaching around 0.7. We have been living in that region, this region where the dark energy dominated. So due to expansion, the general density is going down all the time, and this constant dark energies start to dominate. And this means that, for example, we are now those structures which are in supercluster scales. In the future, they will not be necessarily found anymore, and because of this dominant dark energy part force. Then we have, if we look to say some kind of spherical system, that kind of system where we have mass, and it's possible in that using the frequent cosmology and Undersea model, we can define some specific regions and one that kind of specific region is that limit where this gravitational attraction and this dark energy repulsive force are equal. And that radius we called zero gravity radius. And we can say that inside this zero gravity radius systems are found, at least in this mode. It's possible that the expansion still cause that in the future it's not found anymore, but at least at the present it's found. So in practice it means that there is a velocity component which inside this region velocity component is a little bit larger than this outside component because of the expansion. And in this criterion can be used to define the minimum mass density of gravitational bound system and the present level. So we can semantically show that what that means, that if we have this kind of mass concentration here, we can define a different kind of regions around this mass concentration, and one of those regions are, for example, here this is this zero gravity radius. Here, this is the virially side radius. This is the spherical collapse radius, which is coming from the spherical collapse model. And here, this is the most far radius, which is Einstein-Strauss radius, we can call it that way, or it can be called, for example, linear radius. It means that in these physical coordinates outside here, those things which are here, they are really along the Hubble expansion. They are not any way attractive, this local system. So this is actually the region, say that region which was defined by Tuorla et al. In tape, that superclusters. And you can define, using this semantic picture, you can define different regions from this plot using different kind of density. And you use the matter density, you can use matter density, local volume matter density over, for example, the mean matter density, you can calculate that. And you can calculate the local density over the dark energy density, and no, this is almost the same thing than this, over the critical density. And you can find these kind of numbers which correspond these different regions here. So it means, for example, that in this model here, where the omega matter is 0.3, the dark matter density over the dark energy density is 146 times, this ratio is 146. That means that this region is virially side. And the spherical collapse region, we use this kind of overdensity over the dark energy density. And here, the zero gravity radius, we need 2 times of that. And here, that the most distance region we need 0.7. So you can define this kind of overdensities. So we can, in the dynamical picture of the structures, in one end we have large gravitational unbound superclusters, for example, this Laniakea superclusters, defined as a system with inward peculiar velocity components related to Hubble flow. And in the other end, there are clusters of galaxies in an equilibrium kind of configuration. And it is expected that, at least we expected, that between these extremes there is a continuum of structures with different dynamical states. Now it's natural that we have most extremes we have those objects, but between we have also objects. And this is once again this question now that what is the dynamical state of the supercluster. If we know the mass and the radius of the supercluster, we can apply previous approach, to calculate the matter density in the volume around the system and define the characteristic regions, those which I explained, and broadly define the nominal state of the supercluster. And here is just one example where it has been already used for the one supercluster called A2142, and here we have radius, and here we have mass, and these lines are now those spheres which I showed you before, those different regions. There is this is the turnaround regions, there is a zero gravity region, and there is that linear region here. And when Mirk and Marek, they calculated the overdensity, the data that supercluster, they calculate the overdensity, this is the most densest region, or a region of this supercluster. Then they calculate the mass density here, based on the masses of the galaxies there and groups and so on, and taking into account the radius, they find that this region here, the place is here. So it is inside of this turnaround radius, which comes from the spherical columns. And then there is another region also can be defined. For example, this yellow is this which is somewhere between already, probably a little bit outside, but not border level. And this one is 8 times the mean density. That is for example, this is zero, which I talked about here. This I don't remember which color it was here, but anyway, you can define this kind of region. The only thing here is that, and the problem here is that theory or definition of the dynamical properties based on this kind of method, it's assumed a spherical system. And we know that superclusters are not spherical in general, but this core region is quite spherical, so we can use it in core region at least. Then there is another same thing as actually this plot here. We have used it with Pekka Heinamäki, Pekka Heinamäki, and also those other authors we have used also another way. This is actually the same thing, just written in a different way. Here we have this local matter density over the dark energy density as a function of mass and radius of the system. And then we called it lambda sigma-Mach diagram. And you can put those, you can define here different kind of regions. This is same plot as before where you have those curves, but this is done in different way. So here is zero velocity. This is turnaround ratio, turnaround radius by Severol's model. This is the zero gravity radius, and this is that linear radius here. And these are mass lines. So now when you put here, for example, some objects, here is the OMA, these are Sloan-Lippitt-Kaiser groups, these, at least these, which are well-defined objects, and also Boma is very defined cluster, if we take account their size and mass, and put in this map, we see that they are all here very, their overdensity values is high, and they are well inside the thermal ratios, or they are even very precise as these. But then there's something, if you put here, for example, you can estimate the Laniaka supercluster in some level, it seems to be spherical. If you just take that as it is, the Laniaka supercluster place is somewhere here, and this is that linear radius. But again, there's a problem that in general we can use this method because we need the spherical. Okay, now we can speak. So I use now the supercluster from the Johannes incidence field catalog, and I use those adaptively selected superclusters, and there is a total, there is something like this many superclusters, and I start to analyze these, aiming to that is it really is somehow possible to study at least some of those superclusters using that method which And first I take the I found all those groups from each goes to 1,200 superclusters, and I used the dynamical mass, this kind of formula to define the dynamical mass of all those groups, and then I calculate those groups together, trying to find the dynamical mass of the whole supercluster, and then I follow the Ramir's paper and Marek's paper. When they study this specific one supercluster, we use same definition that I calculate this dynamical mass only for the groups which has 5 or more members, because you have less than the dynamical mass is completely wrong, or the scatter is negligible. So I define this way, and if there is and less than 5 members, I just take the median mass of the such groups. So that was that kind of assumption for those smaller than 5 groups. And then there's also single galaxies, and we assume that there exist anyway some galaxies, but we have magnitude limits in our sample, so they are definitely, we assume that they are also small groups, and then we also assign these single galaxies with this minimum mass here. And then we put something like 10% internal intracluster gas to the mass. So these are very good definitions for the dynamical mass, but same time the masses are huge, so these kind of small errors make here it's not so then there's some selection effects which we take account also, and then there's those all 1,200 superclusters. Then we know for the previous studies that these even we have used this luminosity density method, and there's all those biases related to the magnitude limited sample has been taken account using weighting parameters, and then as well as we can. Even that was taken account. They said for the clusters which are more power rating, 300 megaparsecs, there seems to be still some kind of bias a little bit related to these corrections, Goodness corrections, so we cut the sample here. Then we see that there's still some kind of bias relating to the luminosity, and we see that these are a little dimmer here than here, so I put this kind of link also here, so I take only these superclusters here. Then I put this kind of link related to the richness of the supercluster, because we will use the Minkowski function, the next morphological analysis, and this is somewhat, based on the previous studies, this is somewhat the minimum number of the cards is needed to make some kind of morphological analysis. And when I use these selection effects, here the number of the supercluster reduced to 132. So I draw very more than 1,000 superclusters, and then when I use these, there was only 65. So those other ones are something. I'm not interested in those. So these are straight limits, what you need to put. No, not very straight, but some limits you should use. So the next step was to use the morphology analysis. So obviously for the superclusters, they are not spherical as a starting point. They are pancake type, so they have kind of filament type structures. So now I try to find most spherical superclusters among those 65 superclusters. And for that purpose, I used the morphology information, which was already calculated by, I suppose, Johan in that catalog, and there's those called Minkowski functions, and this kind of safe finder vector K, which is there's two components, K1 and K2, and those you can use these two values to find out is the system spherical, filamentary, or pancake type. And in that case, there's that kind of, if there's a ratio between these two values is larger than 1, that corresponds to pancake type. And for the ideal pancake, this for K1 is 1 and K2 is 0. And if the ratio is between 0 and 1, it's filament type structure. And the ideal filament have 0, 1, or 1, 0, or 2. K2 is 1. And in spherical case, both of these are 0. And it's related, this K parameters, they related also to the of course you can assume already that triaxial axis ABC, but it's not one-to-one correspondence, of course. So here is that kind of numbers. You can see that this was the paper by Sahni et al. There's a nice shown that how these triaxial ellipsoids related these values related these K parameters. And as you see, this is spare, then those both are 0. Then it is spare, but it starts to be a little bit filamentary type. You have these kind of values, and then it goes here. This K1 increase, this is still small, quite small. And if you have a spare here, and it goes through toward the pancake type, then this C goes down and down and down, so it squeezes, the sphere goes like this. And here in this plot you have that here is, you can divide these are spares here, these are K and K1, K2 values, these are those maximums here, and it can be divided with these values, K1, function of K1, K2 values are here, filaments and pancakes here, and spares are here in and here are some figures also, some quite sunny, just get the idea. And here are different kind of combination of these K parameters here, and for example here we have this kind of almost spherical type thing here. And here this has value 0.14 and this has value minus 0.09. And this minus means that if there is a minus, there might be some kind of holes or things. And as you see here, there's also that kind of hole here. But in principle, this is more quite spherical. So I have these 64 superclusters. I assume there's also fourth Minkowski parameter V3, which describes the clumpiness of the system. So if we have spherical system, I also want that it's natural, but I also demand from the data that this should be 1. It means that supercluster has 1 center. So it's not 2 centers or 3 centers as is often for the large superclusters. And then I defined the required that K1 and K2 should be less than 0.05. So that is quite a small number. So it's quite spherical thing actually. And same times I've noticed that if I take this value, all those superclusters which have these K parameters, they are always this type also. So they are not, there's only one clump. So then I start to plot those 65 superclusters in that kind of diagram, and here is the K parameters here. So these are those 65 superclusters, and this color is now the property of that supercluster. So this is the luminosity of those, all 65, how they are distributed as a function of K1 and K2 parameter. And we see, for example, in first that, okay, large K1 and K2 values, okay, and this line here, this divide the systems that way, that these are filamentary type superclusters, and under this line you have pancake type superclusters. All these figures. And then you see that these are filamentary type superclusters which have very quite large K2 values and K2 values. So they are really filamentary type systems here, and they seem to be more luminous than systems which are here, which have smaller K values. So this is the luminosity, those brands of the luminosities. And for the masses, we have same kind of situations, that those most massive ones are those here, those filamentary type with larger K values. And the number of the groups in the supercluster is also similarly, it seems to be so. Volume is same. Diameter of the system is also corresponds, all these correspond to each other. Only mass to light ratio is something similar. So it seems to be so that mass here, which pays our denominator analysis, we believe that it's right. It seems to be, the mass to light ratio seems to be quite high comparing to these other type of superclusters. these dots, these crosses here are now the individual supercluster K1, K2 values, and these 4 dots here, actually these red dots and green dots, these large dots, are those superclusters which K values are less than 0.05. So I found 4 superclusters finally, which are very spherical, and they are here. And these green ones are those which K values are less than 0.03. So most. So, but in principle, these 4, there's those 4. And they are spherical, and they are small. Their diameter is something like 30 megaparsecs, something like that. And they are quite thin. They are not very shining objects in that sense. But it seems to be that there are those. And when I plot these in that plot which I showed before, where you have these zero gravity radius and those zero velocity collapsing radius and this linear radius, those 4, these are graphs and clusters from the slow-orbital star survey. They are all here well-founded region. But here is a zero gravity radius here, and these are those dots. So it seems to be so that they are very close to zero gravity radius. At least one of those is clearly there, and there's some calculations which are not here shown, but in principle, if you assume that system is a little bit flattened, then the zero gravity radius goes a little bit down in this picture. So in principle, if you take this flatness count also, then it seems to be, let's say that these might be bound systems, all these 4 systems, and they are, so the systems of zero radius line are totally within the collapse region. The outer part of system below the line have not been retained down to the zero velocity. So these are completely bound, but above this they are bound, gravitationally bound systems, at least in that mode, this mode. So we conclude, this is not ready this paper yet, but we conclude in this point that we use topological argument to restrict a spherical sample of superclusters as spherical as possible, and we analyze their properties and dynamical state. Our analysis of quasi-spherical superclusters, now we have this quasi-spherical name here because they are not spherical, they are quasi-spherical anyway, shows that they are relatively small, less massive, less luminous, and they contain less galaxies and groups than other superclusters. Quasi-sphericals found here, they can be considered as the largest gravitationally dominated systems found so far. Actually, if we start to think that they are really probably the largest gravitationally bound systems found, because they are huge, they are 30 megaparsec systems. And if you think the clusters are very small compared with this. And from the dynamical point of view, these objects represent intermediate systems between clusters and largest superclusters. It will be interesting to compare these results with the simulations where non-trivial systems are extracted. And due to large mass concentrations in relatively small and spherical region, they might be visible, for example, via general telescopes. Because we have probably also probably some electrons spectrums and so on, they're quite nice configuration, and if you at least if you stack those 4 same size of superclusters together, it is possible maybe to see this universal those. So it is interesting to see this. But really, after those 1,200 superclusters, because the method is restricted only to spherical systems, there are probably other bound superclusters also, but we cannot use this method for those. We can use this method only for the spherical ones. So the result was that we got 4 superclusters. They are found or very nearly found.
Please, questions? Yes?
How can you take a few slides back to this slide where I had all this stuff? Now, in this figure you have those white crosses, right?
Mm.
And the individuals. And there are several white crosses almost at the same piece where you have those 4.
This one. Why that is there? That is because it has small K values here, right? Is it so that probably it's do not. There's an explanation for that. I just because there are several of those which are, but after those restrictions which are used, that the Minkowski force parameter and the scale values. Maybe some of those limitations take but
probably they are really poor.
Probably they are too poor or something like that. But actually this 65 or maybe there's a clumpiness test. It's not. Probably there's 2 clumps here. No, it's all right. I don't remember this.
But they are somehow bad.
They are bad anyway. They do not they don't survive in that strait.
More questions? Please.
In these color plots, there is color in regions where there are no clusters. So how do they
Here.
No, more like in the left side. And up. Yeah.
Here.
There. Yes. So why is there some?
That is related somehow that when I use this grid and this density calculate these values for these, it's such spread here. That you are right that there's nothing here, but because it's little I smoothed these grids where I plot these, so it's just spread there. So the main thing is that you have here these polar regions and you have red regions here. That is that. It's not so accurate.
What is the size of these superclusters compared to the area? Size?
The linear supercluster radius 80 megabytes. So
these are smaller.
these diameter is something like these are diameters, so they are around the
So they are smaller.
yeah, they're much smaller. Radius is something like 10 megabytes. So those superclusters, what I found, their radius is something like, it's actually something like here.
Oh, this 30 megaparsec was diameter.
That's
Then this is approximately like this largest size of this Apple.
yeah. Yeah. But it's spherical system. So in that sense, those are, it sounds at least very nice that they are largest gravitational bound systems found yeah, in the whole universe. So it's
More questions?
So if they are sort of like relatively small structures in the universe, can we say something about their distance? Distance, how far away?
Yeah. We know the distance. Yeah. We know very well everything. What are the objects there and so on. So we can study those. I do not have plot here in those individual superclusters, not the galaxies distribution and so on. But if we found that this source I told you is reliable enough and we can publish this kind of study, then we can study those 4 objects more detail.
But this distance was something like less than 2,000 megawatts.
Yeah. They are somewhere here. I don't know. Remember, this is distance now. So somewhere here.
More questions? If there are no more questions, then thank you very much.